Good morning, students. Today we are going to look at graphs of some functions which you will have to know without the calculator. So these are some parent graphs that you're expected to know as a Math AHL student. So the first one is something that all of you already are familiar with, the linear function, which is of the form y is equal to mx plus c. We all know that m is the slope and c is the y-intercept. C can also be thought of as the initial condition. That is, when x is 0, what is the value of y? So C is also called the initial condition. And depending on the slope slope can be positive and the slope can be negative, slope can be 0, or slope can be undefined. For slope 0, you have the horizontal lines, y equal to 2 or y equal to 4 kind of a line, and for m undefined, these are the vertical lines whose equations are usually x equal to something, x equal to c, somewhere c is a constant. When I write y is equal to mx plus c, I'm thinking of the basic line y is equal to x and all kinds of transformations possible on the line will make it mx plus c. So depending on the values of m and c, I can either have a vertical stretch, a vertical translation, a horizontal stretch, or a horizontal translation, isn't it? For example, y is equal to x minus 2. I can think of it as a horizontal translation, or I can think of it as a vertical translation. Let's, for example, draw this and see. So we have y is equal to x, and when I draw y is equal to x minus 2, I can think of the red line as a horizontal translation, 2 units, because so x intercept was 0, and then now the x intercept is 2, so it has moved right. Or I can think of it as a vertical translation and say that the y intercept was 0 and now the y intercept is minus 2. So the same equation is showing us two kinds of translation. Or if I write y is equal to some 3x, and if I compare it with the first line, then I know y is equal to 3x is like a vertical stretch. It's making it steeper. Or I can also think of it as a horizontal compression, that I'm making it's 3 times faster. So for 1/3 value of x, I'll get the same value of y. So both horizontal stretch as well as vertical can be thought of in this. So that's my first set of graphs which all of you are familiar with. The second kind of function that we all are familiar with is the quadratic function. So y is equal to x square is a parent function, and every other transformation of quadratic is ax square plus bx plus c. So when I write ax square plus bx plus c, I'm including all types of transformation. I can think of it as a vertical translation. I can think of it as increasing the slope or making it a vertical stretch. I can write it as a vertex form and think of it as a horizontal translation and a vertical translation and a horizontal stretch. Or I can think of it in some form like this. I don't know, maybe some b times plus c. So I can think of it as also a horizontal compression. So the way I write the quadratic, I can think of it in different forms, correct? Or if I write it in the intercept form, a times x minus p into x minus q. Again, I can think of it as horizontal translation of the roots. Rather than being at 0, it is now at p and q. So therefore, horizontal translation. So the general form of a quadratic represents all forms of transformation. In the previous video, we also saw exponential equation. In the general form, we said here this where A represents some form of the slope or reflection about the axis. B represents the slope and it also represents reflection about the y-axis. This is about the y-axis and this is reflection about the x-axis, and C is the vertical translation. If you have any doubts, what I would ask you to do is try different values of A, B and C. Look at only positive values first and see how it changes, and then try negative values, try less than 1, try more than 1. So play around with the values of ABC and see what happens to the graph for you to understand this. B, the base cannot be negative. For the kind of exponential equations we are looking at, we are restricting the base to positive. And what is the graph looking like? Well, the graph looks like this. If B is greater than 1, and the graph looks like this. So this is a growth function and this is a decay function, and this happens when B is greater than 1, sorry, not 0. B is always greater than 0, and this happens when B is less than 1. A fraction when multiplied with itself goes on becoming smaller and smaller. A number greater than 1 when multiplied with itself becomes bigger and bigger. So I have two kinds of exponents, an exponential growing function and an exponential decay function. Okay, and that's the graph, right? We forgot to graph the quadratic, but I'm sure all of you know. So there are quadratics with either 2 roots or there are quadratics with a single root, or there are quadratic functions with no roots. They don't intersect the x-axis, and I'm drawing all the quadratics which are facing upwards, but we know that there are also quadratics which can be facing downwards. So as long as they are parabolic in nature and they either are having 1 root, 0 root or no roots, that's fine. Those are the different forms of quadratic graph. So we also now know how the exponential graph looks like. The fourth kind of graph that we have to be familiar with is the logarithmic function. So logarithmic function is the inverse of exponent, and the basic shape of the graph is this. This is ln x, parent function, and every other log function is a transformation of this. So it's log a times log of x to the base b plus c. So b can only be positive, like the exponential, base is never negative, but a and c can take positive, negative values and start changing them like in the previous video, and you will realize how the graph transforms. It translates, it compresses, stretches, reflects. The next is the square root graph. Again, we are primarily looking at the shape of the parent function. So this is root x. Every other function of square root will be a transformation of this. For example, if there is square root of x minus 2, what will happen? It's a horizontal translation. So instead of starting at 0, it will start at 2. The shape will remain the same, but it will be translated to the right by 2 units. What if it is 2 root x? Well, it's a vertical stretch. So it will... Now, how do I show the vertical stretch to the examiner? Well, mark a point. 0, 0 will remain as it is. But when x is 1, y will be 2. In the original function of root x, 1, 1 would be a point. But in 2 root x, 1, 2 is a point. And the shape. So this way the examiner knows that you have understood what is 2 root x. What kind of transformation is it doing? What if it was square root of minus x? Oh, well, it's a reflection. That means now whenever x is negative, I'll be able to take the square root. because negative of negative becomes positive. I cannot take square root of negative numbers. So this function will be a reflection along the y-axis. So shape is same, but reflection. What about minus root of x? Well, it will be a reflection along the x-axis. This is minus root of x. So whatever was positive earlier now is negative. Okay. What is the next kind of a graph that I need to know? X, all the even powers of x. Now we have to remember that all the even powers, let it be x square, x raised to 4, x raised to 6, and so on, all of them have an end behavior of either looking up if they are positive leading coefficients, or if they are negative leading coefficients, that means they are leading with a negative sign for the highest power, then they will be facing down. Let me show you some graphs. For example, if it is x raised to 4, that's how it looks, facing upwards. Minus x raised to 6, facing downwards. But do you see that nature which is similar to the parabolic shape? But if I include more terms, definitely there will be some terms that will be introduced. But if you still look at the end behavior, because it's positive leading coefficient, it's still looking up finally. At the end, there is no change, still looking up. So do you see that the end behavior means after all the terms, what happens at the end? It is still looking upwards. So that's one of the properties of even function. Similarly, if it's a negative leading coefficient, let's add some of the terms. Minus 3x cubed plus 2x square. If I look at the graph, it is finally looking downwards, right? It doesn't matter whether it is facing up or down. It is looking down because it is a even function. So that's the shape of an, so all even functions either look up or they look down. What about odd functions? So like x cube, x raised to 5, x raised to 7, what happens to these kind of graphs? So if we graph x cube, we realize that one arm is up and one arm is down. Unlike x raised to 4, where you saw both arms were up, or x raised to minus 6, where both arms were down. So that's what the odd function does. Even if I add terms to it, you will see that it continues behaving with like the one arm up and one arm down. See, this is the basic structure of the end, or the end behavior of the odd function is always like that. What happens if I change the power to any odd function? Well, that continues. However, as soon as I change the positive leading coefficient to a negative leading coefficient, it changes, meaning it just alters. Everything becomes the other way around. So now again there is one arm up and one arm down, but if you see, it is a reflection of what was there before, right? So that's the nature of odd functions. If I want to summarize it, I say that, yeah, odd functions, they have one arm up and one arm down for positive leading coefficients, positive, or one this way for negative leading coefficients, right? So again, this is something expected for you to know. And 1 by x, reciprocal of a linear function. It's something that you have studied in middle school, your inverse proportionality relation. As x increases, y decreases. As x increases, y decreases. So this is the reciprocal function. Basic structure of what happens when I take reciprocal of a linear. See, do you see the denominator is a linear function? That is what. Same thing even in case of rational functions. Take any rational function. The basic structure of the rational function is going to be very similar to reciprocal, but it will be bounded by a vertical asymptote. What is the vertical asymptote here? Well, vertical asymptote is where the denominator becomes 0. Whenever the denominator becomes 0, the function becomes undefined. So that is the place where there is a vertical asymptote, which means the function cannot take this value. The function can never take the value x equal to 4 by 3. What about the horizontal asymptote? That means where does it approach? Like for example, if you look at 1 by x, as x increases, y approaches 0. So y equal to 0 is the horizontal asymptote and x equal to 0 is the vertical asymptote. Similarly here, what is the horizontal asymptote? So which means what does it approach? So 2x plus 3 upon 3x minus 4 when x becomes very large. Let me rewrite this in a slightly different form and then ask you this question. What happens when x becomes very large? 3 by x becomes a negligible term when x is very large. Similarly, 4 by x becomes a negligible term. So what am I left with? I'm left with 2/3. And that's your horizontal asymptote. That means when x approaches large value, y approaches 2/3. Oh, okay. So x cannot take 4 by 3. As x approaches 4 by 3, it will go to infinity, and then as x increases, y will approach this. What about on this side? Well, symmetric behavior should be there, but I will have to mark the intercepts. When x is 0, y is minus 3 by 4. When y is 0, x is minus 3 by 2. So my graph looks like this. It is approaching 2 by 3 or it is approaching 4 by 3. That's how the graph looks like. So these, what kind of functions are these? Rational functions. You have to know how to graph rational functions without the calculator or with the calculator. Reciprocal of a quadratic. So y is equal to x square. You know how the graph looks like. This is y is equal to x square. I have to know how the reciprocal of this looks like. Well, reciprocal means wherever there is an x-intercept, that will become the vertical asymptote because denominator cannot become 0. And then as x increases, y decreases. Even on the left hand side, as x increases, y decreases. And it is symmetric because of the square operation. The values remain the same on positive and the negative side. And the y value remains only positive because y is equal to x square is only positive. So reciprocal will also be positive. What about y is equal to 1 by x cube? Are we able to, let's look at it. So this is y is equal to x cube. Let's see if we are able to identify how the reciprocal will look like. First of all, when x is 0, y is 0. So when I take the reciprocal, what will happen at x equal to 0? It will become undefined. Your x equal to 0 has to become the vertical asymptote. Okay. What happens on the right side of x? When x increases, y also is increasing. Y is also increasing. So what will happen to the reciprocal? As x increases, the reciprocal will decrease. Okay. What about the negative side? Well, the values are negative, but the behavior is the same. As x is becoming more and more negative, y is also becoming more and more negative. So the reciprocal will be the opposite. As x is becoming more and more negative, 1 by x cube is becoming less and less negative, approaching 0. If you compare 1 by x cube is looking very similar to 1 by x. Now how do we differentiate? Let's graph that and check. Let's graph both 1 by x. Some of you must have already guessed it, but let's see. 1 by x cube. And let's zoom in to the region to be able to see what the difference is. Yeah, behavior is same, but what are you seeing? The blue graph is closer to the y-axis than the green graph. So that means 1 by x is steeper. It is going to reduce, it is closer to the y-axis. 1 by x cube very quickly falls down to 0 because as x increases, x cube becomes bigger much faster. Therefore, it will fall down or reduce to 0 much quicker than the blue graph. That's what you're observing. Blue graph takes more time to reach towards 0, whereas green graph very quickly reaches towards 0. But the shape is the same. So if you are drawing 1 upon x cube as a sketch, the examiner won't know whether you have drawn 1 by x or 1 by x cube. How can you show the value? Well, you can look at these two values are the same, but if you take any other value, like for example at 2, 1 by x will be half, but 1 by x cube will be 1/8. So you can show any one value on the graph, or for example -2. At -2, the value will be -1/8 or -0.125. So that's one way to showcase that your working is correct. Okay. What other graphs do I have to know? Well, this is most of it that you have to be familiar with. So let's recap. You need the linear function y is equal to mx plus c. You know the quadratic y is equal to x square, and then all transformations of it. You have y is equal to x cube, and all odd functions are also like that. Right, all odd functions will also look very similar to x cube, one arm up and one arm down. You have the square root function, the exponential growth or exponential decay. So I'm looking at it as e raised to x or e raised to minus x. And I have ln x. 1 by x, one by x square, and finally 1 by x cube, very similar to 1 by x, so we will not graph it again. So these are some of the graphs that you should be knowing without the calculator and all transformations of this graph.